In this module, you will learn the missing data problems which arise in practice in various scenarios, and the Bayesian method really help how to handle this missing data problems. In this module, we'll talk about missing data analysis. We'll first talk about a little bit of introduction about missing data models, then types of missing data, corrections for missing data in theory, and missing data in practice. So that's the learning objective of this module. Okay, so what happens? Why we see missing data problem is so important? It is well known that on average, about half of the respondents to surveys in political science research do not answer or more than question used in the analysis. And this is actually applied for any social or even some of the medical analysis questionnaire. People don't answer, sometimes because of confidentiality, sometimes because of lack of knowledge. Almost all analysts contaminate their data by filling in educated guesses for some of these questions. Example, for party identification questions, don't know means independent. In US election setup, there are two major parties, the Republican and Democrat, and then the remaining is independent. In Indian setup, it doesn't arise because there is a multi-party. That makes even more complicated. So even if these guesses are correct on average, filling in missing cells of our data matrix in this way biases our regression coefficients, standard errors downwards. When educated guesses are not possible, the standard remedy is list-wise deletion of missing data, eliminating entire observations in a wholesale manner. Valuable information is lost, and severe selection bias effects are possible. So let's now develop some notation to clarify how we handle the missing data problem. So suppose D denotes the data matrix, where D includes independent and dependent variable, D equal to X, Y. We assume that some elements of the data matrix are missing. Let M denote the missingness indicator matrix with the same dimensions of D. Each element of M is a 1 or 0 that indicates whether or not an element of D is missing. Dij equal to 0, if it happens, that indicates the ith observation for jth variable is missing, but that the data could be observed. Dij equal to 1 means that piece of data is present. So Dij is an indicator variable. It is possible that the data cannot be observed. Sometimes a don't know really means that the respondent has no basis on which to provide an answer. Finally, we define D sub obs, that is observation, and D miss, that is D part of the data which are missing, denote the observed and missing parts of the data D. So the D is really together D obs, D miss. There are 3 types of missingness which we incorporate in real world data collection. The first one is called missing completely at random. If the data are missing completely at random, then missing values cannot be predicted any better with the information in D, observed or not. Formally, M is independent of D, so probability of m given d equals to probability of m. A process is missing completely at random if, say, an individual decides whether to answer survey questions on the basis of coin flips. If independent are more likely to decline to answer a vote, again in the connection of the voting, where we had three parties and then independent is the third party, preference or party ID question, then the data are not missing completely at random. In the unlikely event that the process is missing completely at random, then inferences based on list-wise deletion are unbiased, but inefficient because we have lost some cases. Three types of missingness as we mentioned. The next one is missing at random. If the data are missing at random, then the probability that a cell is missing may depend on d obs. But after controlling for d observation, that probability must be independent of d miss. In other words, the process that determines whether or not a cell is missing should not depend on the values in the cell. Formally, m is independent of d miss, that is probability of m given d equals probability of m given d observation. For example, if democratic identifiers are more likely to refuse to answer the vote choice question, then the process is missing at random, so long as party ID is a question to which at least some people respond. If data is missing at random, then inferences based on list-wise deletion will be biased and inefficient. The next is the non-ignorable missingness. If the probability that a cell is missing depends on the unobserved value of the missing response, then the process is non-ignorable. Formally, probability of m given d cannot be simplified. A standard example is individuals' responses to income questions, where high-income people are more likely to refuse to answer survey questions about their income, and other variables in the data set cannot predict which respondents have high income. If your missing data is non-ignorable, then inferences based on list-wise deletion will be biased and inefficient. And multiple imputation algorithms that we will talk next won't be a much aid. So now we'll talk about multiple imputation of missing data. The multiple imputation involves imputing m values for each missing item and creating m completed data sets. Across each of the m data sets, if uppercase M sub ij equals 1, then d sub ij will be the observed data, and if mij equal to 0, then dij will be an imputed value. The imputed values for the data set are based on our guesses about the value of mij together with summaries of our uncertainty regarding the missing values. For each imputed data set, you perform whatever statistical analysis you normally would. Then you average your results over the m computed analysis. So let's talk about calculation of quantities of interest. To ensure some quantity of interest, say q, such as the variable mean or regression coefficient, the overall point estimate q star of q is the average of the m separate estimates q sub j. That is, q star will be sum of qj over m, sum from j from 1 to m. Let SEQ sub j denote the standard error of q sub j for data set j, and then SQ square is the sample variance across the m point estimates. Then the variance of the multiple imputation point estimates is the weighted average of the estimated variances from within each completed data set plus the sample variance in the point estimate across the data sets. Again, go to your notes to look at the formula using the appropriate notations. So the weight is a function of the number of data sets, so that if m is infinity, then it would be a straightforward average of the two sources of uncertainty. And there is a formula to calculate that quantity, which you will find in your notes. Now, there is a specific model we'll talk about called King et al.'s and others imputation model. To implement multiple imputation, we need a statistical model that we can use to sample missing values. There is a program called Amelia developed by King, and our most extensive R alternative. We assume that the data are missing at random, conditional on the imputation model, where the model is defined to include the variables that provide information about the missing data process. King's missing data program is based on the assumption that all of the variables in our model are jointly multivariate normal density. King also argues that in most cases, the multivariate normal density is a very good approximation, even if some of our variables are ordinal. Stated more formally, King and others assume that for each observation I from 1 to n, d sub I denotes the vector of values for the p variables, including the dependent and independent variables. The likelihood function for the complete data set can be easily expressed as product of the individual density. Say L of mu sigma will be the likelihood function, where mu is the vector of p means and sigma is a p cross p dimensional variance covariance matrix that provides information about how values of independent variables depend on one another. If we assume that the data are missing at random, then the likelihood function for the observed data can be written as product of individual normal with di obs given mu I obs and sigma I obs, where obs stands for observation. King and others note that this will be a tough likelihood to work with because each observation is likely to have a different combination of missing values. So his imputation model states that the multivariate normal model implies that each missing value is imputed linearly. That is, we can simulate a missing value in the way that we would usually simulate from a regression. For example, let d sub ij star denote a simulated value of observation I and variable j, and let d sub I minus j denotes the vector values of all observed variables in row I except the j. Then the posterior distribution of the coefficient b sub minus j from a regression of dj on d minus j, which can be calculated from mu and sigma can be used such that d sub ij star is di minus I comma minus j and b minus j plus ei star. An alternative way to think about this is to imagine a multivariate normal distribution. An imputed draw from the multivariate normal distribution is the draw from the slice of the distribution for d mesh corresponding to the value of d obs. So let's talk further about the missing data algorithm. Gary King at Harvard has a very easy to use program called Amelia, now available in R package, that creates data sets with imputed missing values. The program is designed to read in a raw data set with missing values and outputs in m new data sets with imputed missing values. You then run your analysis on the m imputed data sets, take averages of coefficients and standard errors as discussed above, and that's the way we develop the algorithm. Rather than using a small number of multiple imputed data sets, one might incorporate a multiple imputation algorithm into your gift sampler. Taken an independent draw from the multiple imputation data set with each iteration of your program. The advantage of this is that the posterior standard errors for regression coefficients already summarize all of the uncertainty about the process for the missing data and the uncertainty about the coefficients themselves. The disadvantage is that the imputations will be much slower and you will have to check for convergence. In your notes, you will find a schematic diagram of the missing data algorithm, and that figure is taken from King, Honecker and Blackwell paper, and that gives some clear idea about how the algorithms is performed. So what you have learned in this module is how to handle different types of missing data problem using Bayesian methodology. We learned different types of mechanisms, for example, missing at random and various other missingness and multiple imputation. These are very useful and crucial whenever we have missing data in real life problem, and our goal is to estimate or inference for the parameters under the missingness structure.